Welcome to Module 7A in our series on artificial intelligence. This module addresses image processing for machine learning. Specifically, it's going to teach us to develop a machine learning algorithm that recognizes handwritten digits 0 through 9. Now, I want to begin with one question, which is how could an algorithm detect a handwritten number, for example, the number 4? And let's assume here that it's not necessarily an AI or a machine learning based algorithm. One option would be a structural method, right? We could look for one vertical line, one diagonal line, and one horizontal line, and try to detect the number 4 that way. However, there are other numbers, for example, if we write the number 7 that way, that also have the one vertical, one horizontal, and one diagonal line. So although we could potentially get it to work, it's not necessarily foolproof. Another option would be a geometric method. We could say, a lot of 4s have this triangle up top, so we could look for shapes, closed shapes whose angles add up to 180 degrees. But like I already showed over here, not all 4s have those triangles, and there are some weird ways of writing something like a number 8 that could potentially include a triangle. And although this is not commonly how it's written, I think in context most of us would understand that that's meant to be a number 8. A third option would be to count the number of strokes, right? Simply look for something where it's 1, 2, 3 strokes needed to write it. However, that's probably less reliable than the other two methods we discussed because there's plenty of other numbers, including the number 7 again, that only require 3 strokes to write. So the answer to the question is that some of these could work, but perhaps not as reliably as we want them to, and that's why we're going to investigate machine learning. Now, a couple of other questions, corollary questions that we'll ask here and answer during the module include, how do we isolate the defining features of a digit? How do we convert an image into the types of numerical inputs that a neural network can accept, can practically use? Is the simple perceptron, which is what we used in the most recent modules, the network structure, is it sufficient for this task? Or do we need something more complex? The answer is yes, we do need something more complex. How do we configure a neural network or a machine learning algorithm to achieve the best results? And what kind of performance can we expect based on what we know so far? Essentially, the neural network structures and machine learning algorithm tools we have in front of us, as well as obviously the type of computer, a pretty standard PC that we'll be using. Now, I want to note that different terminology is used to describe neural networks between different textbooks and sources. So I want to establish how we're going to use that terminology here. We divide feed-forward neural networks into 3 categories based on the number of layers that they have, or essentially the number of hidden layers that they have, 0, 1, and 2+. So the perceptron type network has no hidden layers with a single output layer. Now, sometimes the term simple perceptron is used to describe this type of single layer network, and perceptron can kind of overlap with shallow networks, but I'm not going to use that term as such here. And often we assume for perceptron that unit step activation functions are being used, but again, that terminology is really not important for this module. We want to focus on shallow networks. So a shallow neural network is one with a single hidden layer as well as a single output layer. And anything more complex than that would be a deep learning neural network with multiple 2 or more hidden layers as well as an output layer. These figures support the descriptions from the previous slide. We have the 3 neural network architectures in question. First is the perceptron. So we have a series of inputs that are fed to a single output layer, which then generates the final outputs. We have a shallow neural network, which accepts some inputs. Those are given to a single or first hidden layer. The outputs of that are then passed to the only output layer, which generates the final output values. Third, we have our deep learning neural network, where the inputs are supplied to a first or initial hidden layer. The outputs of that are then passed to a second hidden layer, and the outputs of that are then supplied to the output layer, which generates the final, the terminal outputs. Now, we could inject additional hidden layers either here or here, between layers 1 and 2, or between 2 and the output layer, to make our deep learning neural network even quote-unquote deeper. Next, we have a table which compares and contrasts some of the characteristics of these 3 neural network architectures, right? We have the 3 in question, the perceptron, the shallow neural network, and the deep learning neural network. I don't think there's any need to discuss the number of hidden layers. Again, we all understand 0, 1, and 2 or more. This, as far as our terminology is concerned, is the main differentiating factor between these 3 architectures. I don't think we need to discuss the structure at length, as the figures from the previous slide did a pretty good job of drawing those comparisons. Next, let's talk about behavior complexity, or how complex of a system each architecture can represent. Generally, perceptrons are used to represent the simplest systems, and deep learning neural networks would be used to represent the most complex systems. So the amount of complexity we can mimic increases as we go down. Next, we discuss training time, which generally increases as we move from top to bottom, going from simple perceptron down to deep learning neural network. Now, a lot of this is associated with the assumption that deep learning neural networks will use more neurons and more synapse weights than the simple perceptron. If you had a perceptron with 10 to the 10 neurons in its output layer and a deep learning neural network with only 100 neurons, one would assume that this would train a lot faster. Next, let's talk about its hierarchy. Obviously, the deep learning neural network is the one that is most hierarchical in nature. We're going to assume that we have nonlinear activation functions for all three of these, with the exception being the simple perceptron, with that adjective simple sometimes referring to the fact that it only employs linear activation functions. But again, that terminology varies from source to source. Let's discuss some example applications of these various architectures. The perceptron is really good for simple classification problems as well as regression problems. A shallow neural network is good for basic image recognition, like the type that we're doing in this module, recognizing digits 0 through 9. But for anything more advanced, we talk about generative models, large language models, you're most definitely going to need a deep learning neural network. Now, the final column, what does X or question mark mean? It's asking us whether this type of architecture can represent an exclusive OR gate. And we saw in previous modules that no, the perceptron, assuming that it has access to only linear activation functions, cannot represent the XOR gate because that behavior is not linearly separable. We do expect the shallow and the deep learning neural network to be able to mimic that behavior, which we discuss on the next slide, right? So again, we have seen that a single layer or a simple perceptron cannot model certain functions. For example, it fails on behaviors that are not linearly separable. But do those limitations apply to shallow neural networks, to the case where we have at least one hidden layer? And the answer is not necessarily. So the universal approximation theory, check out the link in the top right-hand corner, states that a neural network with just one hidden layer can approximate any function, given appropriate or sufficient network structure and architecture, a sufficient number of neurons, and appropriate activation functions. Generally, this means both linear and nonlinear types. The universal approximation theorem depends on several assumptions. First, that the target behavior is continuous and not purely random, right? A neural network is not going to be able to mimic or represent random behavior. The input space must be finite, so we must have some reasonable range of inputs to consider, and the activation functions cannot be restricted to linear types only, as is often associated with the simple perceptron. However, this theorem does not do several things. It does not tell us how many neurons are needed. It does not ensure that the required number of neurons is even practically feasible, right? That number could be massive. It could be a trillion, quadrillion, quintillion. And it doesn't guarantee success under varied training conditions. It may be such that training only succeeds under idealized or narrow conditions. For example, there could be a very small set of initial conditions, initial synapse weights that fall within the region of attraction for the global minimum. The universal approximation theorem suggests that shallow neural networks may be sufficient for image recognition, the digit recognition 0 through 9 that we discuss in this module. But before we train any model, we must first prepare the training images appropriately. And this requires us to do several things. We need to reduce noise associated with the environment, things like shadows, if there's movement, etc. We need to extract important features to minimize the effect of non-relevant information on training. For example, the thickness or color of a pen stroke may be irrelevant to training when we're trying to identify these digits. We need to standardize the presentation such that all training images may be vectorized with a standard shape and orientation, as well as scaling and perspective. So examples would be perspective correction and geometric normalization. So let's take a look at an example of how to prepare an image for machine learning or for training. Now, this is not the only way to achieve this goal. However, I do think it's representative of popular methods, and it provides a good starting point for those of you with interest in image recognition via machine learning. So how did we do this? The first thing that I did was I downloaded this image of a 4 from the web. You can see it's slightly off axis and seems to be printed on the side of this gear or some sort of a mechanism. Now, I did cheat a little bit and manually isolated the symbol. I probably could have done this in code. It would have been a little bit complicated, and more importantly, it would have made this module pretty long, and I didn't want to sacrifice that time. So the first step of our actual code was to convert the image from color to grayscale. Now, why did I do this? Because the color information just really isn't important to this application. It's not an essential feature. We can still recognize the shape of the 4 regardless of whether it's in color or not. Continuing with that simplification, we convert the grayscale image to black and white, and that facilitates the 4th step, which is applying edge detection. We'll talk more about that in one sec. The 5th step was to maximize the height to width ratio via rotation. You can see that this is slightly off axis, and now we have it standing upright. And for that, I used an observation, right, that most digits, when they're in their proper orientation, exhibit a maximum height to width ratio, and that worked relatively well. Next, we eliminated any unnecessary white space, cropping it like this. This makes sense because generally we don't want extraneous information in our image. And then finally, in order to provide a standardized image shape, we expanded the sides to make it a square. And so what this did was provide us a set of labeled training images with a standard level of detail, shape, and orientation, with the digit directly in the middle of the field of view. So now let's go back to discussing edge detection. Edge detection is essential to preparing images for machine learning and training. It helps us to extract the most informative structural features, the most important features of an image. In digit recognition, so aka this example, it reduces the impact of the pen stroke width, standardizing the digit, the shape comparison. Different training samples may have been generated by different processes by different people, and so they may vary in the thickness of the strokes, and filtering out these differences, and that's what we use edge detection for, ensures a more consistent model input, or a more, to use the phrase, apples to apples comparison between those training images. Edge detection is relevant to many different image recognition problems overall. It allows an algorithm to isolate a specific object as well as its boundaries within a potentially complex field of view. For example, a self-driving car may use edge detection to determine whether there's a pedestrian crossing in front of it. So let's quickly demonstrate how to prepare an image for machine learning or for training in Python, since we'll also be using Python for machine learning. And you'll see the links to the right allow viewers or users to download the source code. There's 2 versions. Up top, we have the Google Colab project. You can use that link or the QR code to the left. I also have a copy of the source code available in my Dropbox, and you would use the QR code to the right. If you're not familiar with Google Colab, I strongly encourage you to try it out. I think most of you that have experience with Google Colab will see that it's probably the easiest way to access my code and to run it. You don't even really need an IDE on your computer. You can run it straight from the browser. Now, there's 2 important scripts or Python files within the project. One is the library image processing, and it defines the methods that perform the specific image processing tasks, such as edge detection or convert to black and white. And then you also have the main script, and so that's the main executable that calls methods from the library up above. Now here you can see an example of what the Google Colab project will look like when you open in your browser. Again, really straightforward. It makes it easy for anyone to run this example in their browser, but the scripts must be run in order. What you'll see is that there's 2 scripts. The first one actually takes files from my Google Drive and uploads it to the content folder, or the virtual content folder shown on the left-hand side. You need to run that script first, or else you won't have the library or the test image available. Once you've done that, you can use this button here to run the main executable. Now, if you compare the Dropbox version and the Google Colab version, you will see a few small differences. Unfortunately, Google Colab doesn't support certain libraries, especially when it comes to displaying images, but it's really not a big deal. Now, after you run the main script, you'll see that all the images will show up at the bottom, so you will have to scroll down. And if you note, these should look very familiar. These are the same images from 1 or 2 slides back. So let's take a look at the code. There's really not too much to see here. The main script essentially just calls methods from my library. So we load all of our necessary libraries, including the one that I made. We get the path for our test image, which is within that virtual content folder. We use the pillow library to load the image. We convert it to RGB, eliminating any transparent regions. We then call the convert to black and white method from the library I created and display the image. We then call the apply edge detection method from the library I created and display the image. We then call the rotate optimally method from my library and we display the image. We then use the get non-white bounds method from my library and we crop it appropriately and display the image. finally, we use the make image square method from my library and display the image. So pretty straightforward here. So I want to spend 1 second talking about documentation. Let's say you're reading through my code, you see the PIL, the pillow library, you see some of the methods called from it, and you don't really understand what's going on. Don't just keep moving. Take a second, search for that library online. Almost all Python libraries have amazing online documentation, and just read through it real quick. You'll see that 99% of the time it provides a clear overview of the methods you can call and exactly what inputs you need to supply to those methods. So I think this is one important habit you can teach yourself if you want to get better at this type of AI work. So let's provide an overview of the library that I created. I'm just going to discuss the methods. I'm not going to go and look at any code. I think that most of you should be able to understand the code. So the first method is convert to black and white. It converts an image to grayscale, and there's a command for that. And then it applies a grayscale threshold, essentially a value, to produce a matrix containing binary black or white values. If a given pixel has a darkness value greater than X, it becomes black, less than X, it becomes white. We then apply edge detection. This is probably one that's more interesting. So what this does is it takes the original matrix and it creates one copy that's shifted down by a single pixel, and another copy that's shifted to the right by a single pixel. Then it goes through element by element and it compares them. This element to this down here, this element to this over here. Any place where there's a mismatch, that would indicate an edge. A mismatch with either the one to the right or the one below it. We then have get non-white boundaries. It identifies the bounding box that contains all the non-white pixels, trims all the dead space, and this is not super efficient. It essentially uses a search going from the beginning to the end of each row and looking for the first box that contains a non-white pixel and the last box that contains a non-white pixel. We then rotate optimally. This also is not super efficient. We could probably make it more efficient. It takes the original image, rotates it by a small incremental number of degrees, measures its height to width ratio, rotates again, measures its height to width ratio. I think the way that I have it set up, it increments by 2 degrees every time, and then simply saves the value which maximizes that height to width ratio and returns that. Now within that, we also trim all of the additional white space. And the last method is make image square, and essentially what this does is it adjusts the image dimensions by padding either the height or the width as needed to produce a square image. So let's say the height is greater than the width, then you would expand the width to match. Vice versa, width is greater than height, then you would expand the height in order to match. Note that the training data we'll be using for this example that we acquired from the MNIST online database, it's pretty clean and it doesn't really require this level of image preparation. However, I still think it's important to go over this process as it may be needed for future projects. The next question that we need to ask is, how can we convert an image to a form that a neural network can accept and understand? And there's a couple of corollary questions that go along with that. One is, well, what kinds of inputs can a neural network accept? Really, an array of numbers, an array of numerical values. The second corollary question is, how much information is contained within a single pixel of an image? And the answer, at least in my opinion, is not very much, right? The real information is contained in the relationship, the spatial relationship between those pixels. So many of you may be thinking, well, why not just take the image, assign numerical values to each one of the individual pixels, and supply that to the neural network? It's not a great idea because each number doesn't really contain very much relevant information. So the third corollary question is, how can we provide an apples-to-apples comparison between different training samples that may have different sizes, may be oriented differently, etc.? And the answer is to extract relevant features and then supply information about the presence of those individual features to the neural network. Traditional neural networks are designed for numerical input. We already talked about that, not raw images. So again, returning to the question from the previous slide, how can we train them using images? Or some version of that. We convert the image into a matrix or an array of numerical values using a process called vectorization. But this matrix can be very large, especially if it contains a value for each pixel. There could be thousands or millions of them. Now, the question is, can we reduce this size? And I would take it a little bit further and say we have to reduce this size. And again, we said a second ago that an individual pixel doesn't really contain very much information. So one common solution to reduce the size of this visual data is to use a convolutional layer, or to use multiple convolutional layers. Now, this is a topic that we are going to discuss in depth in later modules, but not right now. For now, we're going to apply a simpler spatial averaging method, one that quantifies the state of an image or a sub-image in terms of the percentage of pixels that are black, aka on, or white, aka off. Next, we discuss how to implement vectorization via spatial averaging. Over here to the right, we have a number 3, and we're going to use this to demonstrate the process. The first thing that we do is divide the image into a certain number of regions. And the way that we do this is we divide the image vertically into n vertical regions. So there's 4 of these. And then we divide it horizontally into n horizontal regions. Okay, so in this case, both numbers happen to be 4, but they don't always have to be equal. Now we're going to call each one of these regions a sensor or a sensing region. Each one of these regions provides a single numerical value to the neural network. So we've already achieved a pretty significant amount of simplification. Let's say before this were a 100 pixel by 100 pixel image. Okay, we've reduced that to really only having to supply 4 times 4, 16 numerical values to the neural network, as opposed to 100 times 100. Now each value represents the percentage of a sensor's area that's covered by the pen stroke or covered by the dark region. We begin with 16 sensors arranged in a 4x4 grid. Now obviously this matrix would be flattened out and supplied to the neural network as an array, but that's really more semantics. And we use a method that I developed called apply vectorization within the image processing library. So let's take a look at the example over here to the right and see how the numbers of this matrix are generated. So let's first look at the areas, the sensing regions, that the number 3 doesn't touch. So what are those? We have this one up here, we have this one up here, we have essentially all 4 of these. And so you can see a 0 value, 0 value, 0, 0, 0, 0. Now let's look at a region that's pretty heavily covered. I would probably use this example right here. This is pretty fully covered by the pen stroke. And so we see the corresponding value is 0.55. Over here, right, we see that only a small sliver of the number 3 reaches into that box, and so we have a very small but non-zero value of 0.03. So these values are expected to vary between 0 and 1.0. 0 being the case where the number 3 or the pen stroke doesn't enter that region at all, and then 100% would be the case where the pen stroke completely covers the entire region. Next, let's discuss the neural network design or the neural network architecture. As stated previously, this image recognition problem is probably too complex for a simple perceptron, at least the way that we defined it previously with a single output layer and an assumed linear activation function. Instead, we're going to use a slightly more complex model, a shallow neural network, one with a single hidden layer and single output layer. Now normally we don't refer to the inputs as a layer because they're simply values and they don't have a summing operator that's applied or an activation function. So how do we choose the number of neurons in each layer? Because there's really 3 questions we need to answer when we define architecture. One would be the number of layers. We've already determined that. The shallow neural network will have 2. The interconnection of those layers, and we're going to assume fully connected for the time being. And the third question being how many neurons are in each layer. Now for the input and the output layer, that question is relatively easy to answer. Our vectorization method for the image yields 16 values, so we'll have 16 inputs coming into the neural network. Our output layer needs to generate 1 output for each potential classification. We're trying to classify the digits 0 to 9, so 10 neurons are needed in the output layer. Now for the hidden layer, this question is a little bit more difficult to answer. We're going to use 32 neurons, but we need to back up that answer. So let's take a look at our neural network in greater detail. We begin on the left-hand side with our raw training image. In this case, it's a number 3. You can see there's some noise in the background. In order to reduce the effect of this noise and isolate or highlight the features that we're most interested in, we apply image processing, the same type of image processing that we discussed at the beginning of this module. Once our image is processed, we can apply vectorization, the objective of which is to take this image and generate a number of numerical values that the neural network can accept. Now let's assume we're still using the same 4x4 sensor grid that we proposed earlier, and that would generate 16 inputs to the neural network. Now the neural network is composed of 2 different layers. We have the hidden layer that's shown in red, and we have the output layer that's shown in gold. The hidden layer employs 32 neurons, as well as a rectified linear unit activation function looks like that. We'll talk more about that later. The output layer only employs 10 neurons, and a sigmoid-based activation function. We'll talk more about that later as well. Now, where did this number 32 come from? We'll talk about that more in a second. Where did this number 10 come from? Well, that's pretty straightforward. Since we're trying to recognize digits 0 through 9, that essentially means we have 10 different classifications. How do these classifications correspond to the digits? That would be dictated by how we label the training data. Now, I haven't shown all of the synapse connections between neurons, but for the time being, we'll assume that it's fully connected, meaning that any output from a given layer is connected to all inputs from the next layer. So now let's talk more about the hidden layer. So the number of neurons in a hidden layer is not well defined as compared to the number of inputs or the number of neurons in an output layer. So how do we decide how many neurons to place in each hidden layer? And for now, let's just focus on a shallow network, so we assume that we only have one hidden layer to deal with. The most common or basic rule would be to choose a value between the number of outputs, so that's the number of neurons in the layer that follows it, and 5 times that number. So that at least gives us a range that we can work with. There's many heuristic methods. There's estimations such as that shown here. The number of neurons in the hidden layer is equal to 2/3 times the number of inputs plus the number of neurons in the output layer, or the square root of the number of inputs times the number of neurons in the output layer. The most effective and most methodical method is cross-validation, where we refine these estimates by training models using different hidden layer sizes, somewhere let's say between 10 and 50 for this specific example, evaluate using k-fold cross-validation, and choose the size that gives the best accuracy without overfitting. So in short, the best way to define the number or the optimal number of neurons to be placed in a hidden layer is to try out different values, test them, and see which one provides the best convergence characteristics. So we've discussed the neural network structure already. Let's spend a minute talking about the machine learning implementation. The first important topic or relevant topic would be the availability of training inputs. So we're using approximately 500 handwritten images of digits 0 through 9 from the MNIST dataset that's available online. And obviously those need to be labeled because we're going to be employing it for supervised learning. Quick note, we actually loaded the images manually as opposed to using the Python library that's provided. Not that that really makes a big difference. Now let's talk about the machine learning algorithm itself, which we implemented within VS Code, obviously using Python and PyTorch. Now, if you remember from a couple modules back, there were several key characteristics that we said define how a machine learning algorithm works, and they're listed here. So the first would be the loss function. What loss function did we employ? We employed the mean squared error loss function, which we've discussed previously. I don't think I need to cover that again. The model that we employed is the shallow neural network. We talked about that at length about 1 or 2 slides back, right? We have 16 inputs coming in, going to a single hidden layer with 32 neurons, and that's fed to a single output layer with 10 neurons. What is our learning approach? What is our learning strategy? We're using supervised learning via stochastic gradient descent with consideration of momentum, dampening, and weight decay. So I know we haven't talked about gradient descent yet, but that is going to be the topic of one of the upcoming modules, if not the next one. And then the application, which I think is pretty evident at this point, would be classification, right? Because the goal would be to generate a neural network, a trained neural network that's able to accept an image of an unknown digit and classify it into one of those categories, 0 through 9. So let's discuss the testing of our machine learning algorithm as well as its performance. Now, the source code. The next module focuses on the source code, which will be reviewed line by line, and you'll also be given a link that you can use to download this source code and play around with it yourself. Now, this example represents a more advanced application of Python and PyTorch as compared to the perceptron from previous module number 6. With regard to results, the image recognition machine learning algorithm, the one that we're going to discuss in the next module, but we introduced in this one, reliably converges across a range of training setups and initializations with an accuracy on average greater than 95% and requiring somewhere between 15 and 25,000 iterations to converge. In summary, this module introduces a shallow neural network for handwritten digit recognition, covering key topics such as shallow versus deep neural network architectures, the universal approximation theorem, image preprocessing and vectorization, as well as Python and PyTorch examples, right? Continuing our emphasis on hands-on practical work. Now, in the next module, we're going to take a look at this source code for image recognition, and this is source code that you can download and play around with on your own.